Spotted, a planetary system information. Welcome to our SETI Live. My name is Franck Marchis, and today we are going to talk about Exomoons information. And we are going to talk about a very interesting system which has been studied using an interesting technique called PDS-70, and the planet is PDS-70c. So, as you know, for the SETI Lives is a weekly series that we have, and we invite scientists to present their research. And today we are very honored and happy to have 3 of them. So let me introduce first of all our first scientist, who is a researcher at University of Grenoble in France and at the University of Chile. And she's the lead author of the article that was published last week or this week. Hello, Myriam Benisty.
Hello, Frank.
Where are you calling us from?
In Santiago. So right now in Santiago in Chile.
Okay. Well, thank you very much for joining us from so far away.
Thank you.
And nearby on my window here, we have Stefano Facchini. Stefano is a researcher at the European Southern Observatory. Hi, Stefano.
Hey, Frank.
And you are located?
Right now, I'm in Milan, Italy, but I usually work in Munich.
Okay. And on the third window, another researcher, but this time at the Center for Astrophysics at Harvard University, Richard Teague. How are you, Richard?
Hi, Frank. I'm doing well.
And you are in Cambridge?
Yes, I'm in Cambridge in Massachusetts.
Okay. And I'm in Prague in Czech Republic at the moment, Charles University. So we are everywhere in the world, and we are welcoming all of you. Today we are going to talk about this very interesting discovery. So let's go straight to the point, Myriam. Your articles have been everywhere. I mean, it's been mentioned in so many places that I cannot count them. Even the New York Times, I heard. So tell us, what is this discovery? Why is it so important?
Indeed, we've been very lucky with the media coverage. So what we found is that we found for the first time evidence for circumplanetary disks, so for material surrounding a giant planet. And in this material, moons and satellites will be forming or are already being formed. And this is something that, of course, we expected because we know that giant planets have a lot of moons. And also we expect them from the theoretical point of view. But this is the first time that we can actually really observe and have this unique laboratory to test our theoretical ideas.
So what does that look like? How do you find this kind of stuff?
Okay, let me share some slides. So how does it look like? It looks like this. So we have here an observation that we obtained with the ALMA interferometer that Richard will discuss later on. And what you can see here is that we have a young star here that we cannot see actually in the image, surrounded by dust here. And then there is this ring here of material. And in between the inner and this outer ring, what we have is 2 planets, so PDS-70b and PDS-70c. So the planets are not emitted at the wavelengths at which we observe. We got this image, so we cannot see the planet themselves, but we can trace the material around the planets. So PDS-70b is orbiting the star along this orbit, and PDS-70c along this orbit here. And what we found is this material around PDS-70c that emits in the millimeter regime, so we could observe it with ALMA. And this is the signature of a circumplanetary disk.
So what we are seeing here is basically the material around the planet, the cold material around the planet, because we're observing in the millimeter.
Exactly.
That's a good transition to my question. So how did we discover this in those planets first, and how did we observe this interesting system?
Yeah, so we were actually, so before we knew about these planets, we of course know that we have observed more than 4,000 exoplanets around old systems, so systems that have already lost the material in which they were born. But we have been observing what we call protoplanetary disks, so the environment in which planets are forming, so young objects with an age of a few million years. And in this disk, we have found already evidence for the the presence of planets or indirect evidence, for example, this large cavity that is depleted of material, is a natural consequence of the dynamical interaction of a planet. So if your planet is there, it's carving this cavity. So we were looking at this disk, trying to understand the structure of this disk, when we found a blob, basically, in the image. And we look back at the observation and the data that observatories have been getting for decades. And we found that this blob was always there. And this happened to be PDS-70b. So in 2018, using the Very Large Telescope instruments sphere, we detected the first planet, PDS-70b, which is, this was a really great discovery because it was the first time that we could directly image a forming planet. And then 6 months later, another planet, PDS-70c, was detected. And this time it was detected also with the Very Large Telescope, with another instrument called MUSE, through a tracer of accretion of material onto the planet. And once we had found this planet, then it was really natural for us to go, the next step forward was to look at the material that could be surrounding this planet. And that's why we observed this system with ALMA.
So let's talk about ALMA. It's a beautiful name, first of all, because it means soul in Spanish. So I don't know if you, Myriam, want to talk about that, or maybe Richard, describe what is ALMA, yes, what this instrument is doing exactly.
So ALMA is really just, it's been revolutionary in our field of studying planet formation. It's this huge telescope, or an array of telescopes really, in the Atacama Desert in Chile. And basically the main goal of having an interferometer like ALMA is that we want to try and achieve spatial resolutions that are very small. So we want to be sensitive to very tiny details on the sky. And we know that the details that we're sensitive to, or the angular resolution of these telescopes, is directly proportional to the size of the mirror that we're using. So the bigger the mirror, the smaller details we can see on the sky. And when we're looking for things like circumplanetary disks, we need to really have exquisite detail and resolve very, very tiny features. And so when you look at the size of telescopes that you would need to do that, you need to have a telescope which has a dish that's sort of tens of miles in diameter, which is just unfeasible to build as one big mirror. So what we do instead is use an interferometer, which is where we try and synthesize a large telescope by combining lots of smaller telescopes around the place. So with ALMA, we have somewhere between 40 and 50 of these 12-meter dishes, which are shown in the lower right here, and they're sort of distributed over the mountaintop in the Chilean desert. And these are sort of spread out, so you can either have them very closely packed together, so there's only a few meters between the dishes, or we can distribute them over huge ranges, so we have up to 16 kilometers distance between various telescopes. And so when we observe the night sky, each of these telescopes is taking data, and then we can combine them in a very special way to reproduce the image that we see, so what Myriam saw before. And it's really moving to a telescope the size of ALMA that has allowed us to make these observations. Not only are we getting the resolution to resolve the circumplanetary disks, which we've been unable to do before, but simply having 40 to 50 of these dishes means that we're collecting so many photons, we can really start to see very faint objects. And that's also been really one of the major points in this detection, is that we need to distinguish this very faint source, the circumplanetary disk, from the very bright circumstellar disk around it. So that was a large ring in the image before. And ALMA has really just been revolutionary in that. In the last 5 years, there's been a whole slew of amazing discoveries that have been made because we now have access to this wonderful facility.
Yeah, I do remember when this facility was on paper only, and how they were promising us amazing discovery, amazing resolution and sensitivity. And I must admit, despite the fact that I'm an optical astronomer, I'm very impressed by the results provided by this submillimetre array. It's definitely an impressive facility. So why is it located in Chile? Why so high?
So we really need, the trouble for astronomy is that we want to try and bypass our atmosphere. That's the biggest limitation in what we can do, because all the water vapor and just all the atmosphere that we have to look through is going to attenuate any of the emission that we're seeing. It's going to make it look a lot dimmer, and it's going to distort the images that we see. So we want to try and remove as much of that as possible And we can do that by getting as high as possible as we can. So we have some space-based telescopes, so that removes it entirely. But if we need to have a ground-based facility like with ALMA, we put it on a mountaintop and that will get it as high as possible. So actually the Atacama Desert where ALMA is, I think it's the driest place in the world. There's so little rainfall there that means that we're minimizing the effect of any water vapor in the sky that's going to absorb any of the signals that we're trying to observe.
Good. So before I go to my next questions, we have viewers watching us from Colombia, Ireland, Cambridge, UK, Colorado, Yorkshire, in UK again, Florida, Haiti, Louisiana, Canada, and Pune, India, Georgia, USA, and Australia. So everywhere, almost every continent here has been mentioned. So welcome. We are talking about the discovery of a cocoon around the planet, the exoplanet PDS-70C. This is the paper that I recommend you have a look on to learn a bit more about this, or you can also look at the press releases. So you made this remarkable discovery, but what exactly is this discovery? Please, one of you maybe can tell us what exactly can you infer from this tiny blob and these blurry features around it?
Yeah, so what we discovered is some materials, so dust material, emitting very close to the planet. So to go back to the full image that we obtained with ALMA, so this is what we call the circumstellar disk. So that's the disk that is around the star, in which planets, at least two planets, because there might be more planets, are carving this big cavity, big gap. So it's depleted of material here. And then around one planet, we found a significant emission from dust that is associated with the planet, that is really collocated with the planet. And this dust is in a circumplanetary disk. So this disk that is expected through the formation of a planet, through which the planet will accumulate its own mass and accrete its own mass, and also form its atmosphere. And through our discovery, what we can say is the minimum amount of mass, dust mass that we have in this disk, and whether or not it would be enough to form satellites. And indeed, what we found is that we have at least 3 times the amount of mass needed to form satellites like the moon. What we could also say here is how constrained the extension of this disk and whether or not it is consistent with all the theoretical predictions. And we found that it cannot be larger than the distance between the sun and the Earth. And that is what is expected actually from all the theoretical models of circumplanetary disk.
Sorry, I was mute because I have an ambulance passing nearby. So yes, from this image, you infer a lot of information about the system itself. I read in the news that you have a constraint on the size of the moon, on the mass, the total mass of the moon, as you mentioned. But what else can we say about formation of planets and exomoon from one image only? And what is kind of the additional information you will need to extract, to know more about this system? Maybe Stefano, you want to answer to this question?
Yeah, so I'm happy to take this. So indeed, the question you raised is a good one. How much can we learn from one system only? But I mean, to put this in context again, as we were mentioning before, this is the very first observation of humankind of material around the planet that is likely forming moons. So again, this to be clear, we didn't detect an exomoon, but we detected the material that is bound, gravitationally bound to the planet that must be orbiting around it that is likely forming moons. What's very interesting, though, to put this one system into context is the similarities that the system has, for example, with our own solar system. So if we, Myriam, you can move to the slide comparing this one. So if you're looking at like the size of this image, we drew the orbits of the solar system planets. You can see in the very inner regions, there are the rocky planets. And then you have the outer planets, in particular Uranus and Neptune, which are very similar orbits to PDS 70b and C. And then we have the Kuiper belt, which is a belt of big rocks, very big rocks, orbiting in the outer region of our solar system, which are comparable to the big ring in the circumstellar disk of PDS 70. And this system is very peculiar, and we can learn a lot from just one of these objects, in particular because we see that this system has two planets, two massive planets. And we can see, for example, that the inner disks, so the inner regions of the disk, thank you, Myriam, are very dim. They're not very bright. And this is because the two planets are acting as a dynamical barrier of the material that from the outer region is expected to migrate inwards. And this is exactly what happened in our own solar system, where the couple Jupiter and Saturn, so the pair Jupiter and Saturn, damped the outer material and prevented the inner regions to become very massive. And that's why we have the Earth, Mercury, Venus, Earth, and Mars, which are very low in mass compared to other planetary systems. And we think we're seeing exactly the same mechanism in act in one disk system. Again, the last similarity is that the central star is a mass that is very similar to the one of the sun. So somehow, with obvious differences, what we are seeing in analogy of how our own solar system worked. And theoretically, this is telling us a lot about how this starvation works, the fact that a circumplanetary disk that was expected theoretically, we finally see it. So that's the first observational confirmation of a theoretical prediction. And so there is a lot to learn about this one system. But again, the hope for the future is that with this fantastic facility, ALMA, but with also other ones, in particular with the James Webb Space Telescope, which will be launched in a few months, and in the future with the 40-meter class telescopes like ELT and ESO, we'll be able to see more and more of these planets while they are being born, and therefore characterize more and more circumplanetary disks in other systems. So this is one of the many things we plan to do in the future.
Yeah, I think it's remarkable that we are seeing probably here a picture of our own solar system when it was only 6 million years old. Maybe not exactly, but two giant planets like in our own solar system. So by studying those, as you mentioned, we can basically understand the past of our own solar system. And maybe in the center here, one day with one of these new facility, we may see something interesting into something kind of a proto-Earth or something like that as well. And we may not reach the sensitivity, but that's a wishful thinking. We have people joining us from Bangladesh, Massachusetts, Romania, and Puerto Rico. Welcome, and Texas as well. Welcome. We are talking about the circumplanetary disk around PDS 70c. We are going to take some questions from the audience here. So if you want to ask some very interesting questions to our three researchers here who has been involved in this research, please let us know. And I will start with the first question. Someone asked, maybe you could stop sharing the screen so we can see the four of us together. Someone asked how far away this system is and how old is this system, and how do you know the size, the age, and the distance of the system? Who want to take this first question?
I'm happy to take it.
Oh, okay.
Okay, Myriam. Oh, I'll take it. So the system is about 400 light years from Earth. The way we know the distance of the system from us is basically we can see yearly that the star moves just a little bit in the sky, and through a method that we call parallax, we can associate this movement in the sky, which is driven by the movement of the Earth around the sun. So the sky moves a little bit, we can associate to a very accurate and precise distance. And so we know this very well. And we know this distance of the two planets just because by knowing the distance from the star to the Earth, the distance in the sky, we can associate it to a physical distance between the planets and the central star. And that's about, the inner one, PDS-70b, is about 20 astronomical units, which is the distance from the Earth and the Sun. And PDS-70c is about 33, roughly, astronomical units from the star. So, so that's how we know the distances. But there was maybe another part of the question that I missed.
What about the age? How do you know the age?
Myriam?
So there are tracers of, I mean, the age is a very difficult parameter to constrain. And usually you have a very large error bar to the estimate of the age. And so, for example, that one has, we say it's about 5 million years old, but it could be actually 3 or 7, 8. It's really difficult to estimate. In general, we have tracers, for example, through emission lines that can tell us about the age of the system, for example, or we relate the position of the star to the position of other stars in the same cluster, for which we can estimate the age through different tracers. Another way, for example, to do that is to look simply at the luminosity of the objects and try to reconstruct the history of the star through the comparison with models, evolutionary models. But all of this is really, really uncertain. So when we say the star is young, it's because we know that it is young for the fact that it has a circumstellar disk, because we know that circumstellar disks actually disappear within few million years. So usually between 2 and 10 million years, the material around the star has dissipated. So we know that it is roughly a few million years old.
All right, thank you. Richard, we have a question about this image. So this is not an image. This was built by interferometry. So someone asked, but can you give us a bit more details about this, the mechanism to build this image, how you really concretely do it? I'm assuming you use computer, but
yeah,
maybe don't, maybe you don't, maybe you paint it, right? No, you use computer, right?
Yeah, so that's a good question. And I think this was really one of the big challenges in this project, was creating that image. So if you think about a traditional telescope, one that works primarily, say, in optical wavelengths, they work in a very similar way to how a digital camera would work, say on your mobile phone. So you just have a detector that you can take an image of the sky and then you get an image directly. And as I was saying with ALMA, we can't do that because you'd need a telescope that was 16 kilometers wide. And so we have to build it up of separate images. And the way that we combine these images is sort of analogous to imagining if you're trying to record a piece of music. So a traditional telescope would just record the music as you hear it. With an interferometer, we're only able to hear certain notes of that music. So the analogy is that on the sky, we can see set spatial frequencies. So for music, we can only hear very set tones or notes that we hear. Once we combine all these data together, we have a good idea of what the source should look like on the sky. So we know, for example, that it should be smooth, it should have certain sort of structures. Then we can use that information at sort of discrete samples to reconstruct a model that we would expect to see on the sky based on what we've measured. So this is a very big challenge in this sort of imaging domain. And I think a really good example of this is the Event Horizon Telescope. So if you saw the recent discovery of them, of a collaboration imaging a disk around a black hole, that's exactly the same sort of technique where you're combining all these data sets and you're using various different image synthesis methods to combine those signals from all these different telescopes that you know very well how they're distributed to reconstruct this image. And so a lot of testing goes into making sure that the assumptions you make in that reconstruction, all the images are robust. So for this work, we had to go through all different variations of how we could recombine this data, how we can weight different data sets differently to show that no matter what we chose, what assumptions we made, the detection of the circumplanetary disk around PDS-70c was really robust there.
So there is some an algorithm behind it, but you test different hypotheses to confirm the existence of this structure by changing them. And in every cases, you show probably in the paper or to the referee that you get this this structure around the planet, no matter what.
Exactly. We have a really nice gallery in the paper showing all these different realizations and different assumptions that go into it. And you can see that PDS-70C, it sort of changes size slightly from different assumption to assumption, but the signal is always there.
All right. That's good.
Yeah.
Okay. I have a question here. Sorry, I was thinking about this paper at the same time. Yeah, what is it? So, will you be able, that's a question I had too, and probably, but will you be able to see the accretion process in action for proto-rocky planets? Do you have the sensitivity basically for that and the resolution?
So right now to find proto-rocky planets, no, it's impossible with the current instrumentation, but that's really what we want to do with the extremely large telescope that is currently being built in Chile. So for what we call the ELT, extremely large telescope, there will be a first light instrument, so the very first one that will look at this inner region, so really the inner disk that I was showing at the beginning, where we expect rocky planets. So we will look first for the signature of these planets, indirect signature of this planet in the disk, as we were doing for the giant planets. Then with the second generation instrumentation, we will actually, with, for example, what we call extreme adaptive optics, be able to really spatially resolve these regions and look for these planets with high sensitivity. So that's something that we are, of course, aiming for in the next 10, 20 years.
All right. So I have some questions and you can give me a very short answer, okay? First question, would the Event Horizon telescopes be able to take a closer look on this system?
Unfortunately not. That would be fantastic, but the difference in how bright the objects are that we're looking at is a billion. The black hole disk that the Event Horizon telescope looked at was a billion times brighter than what we're looking at. And so we just don't have the sensitivity.
All right. How long does it take to take an image like you show us? Wow, how many hours of telescope have you been used to do this?
I think for this particular image, in total was about 12 hours, 10 to 12 hours of ALMA time. But we are getting more and more data. So we have, other 15 hours of data that have just come to us. So
okay.
we'll plan to look more into it.
So did you request telescope time to observe specifically this target, Myriam? Or did you observe this target is part of a large program or you have multiple other targets?
When we discovered the planet, PDS-70b, so in 2018, this target, the disk was part of a large program where we were observing many disks because we want to find, we know that we have young planets in this disk, so we want to find all of them basically. But now that we have found these protoplanets and there is only this system so far that has this, we have both ongoing, these big surveys where we want to find more protoplanets, and also now all the dedicated studies to really go really deeply into the understanding of this system. So now we are requesting a lot of time on this specific system.
And thanks to this discovery, I'm assuming it's going to be probably easier to get telescope time.
Well, I hope, yes, but it's, the application to telescope time is anonymous now. No, we don't know who is applying for the time, which is fair. So everyone can use the beautiful image and apply for more time, which is a great thing.
Oh, yeah, True ISO also now is doing anonymous.
But
so.
in the future, of course, there will be more observation of this system, whether it will be from our team or another team, we will know much more.
So you mentioned JWST. So can you tell us more what instrument will you use to get information about this specific system or this specific cocoon on PDS-70C with JWST? You have an idea already?
I can take this, I think. So there are different instruments on JWST. So PDS-70 will be observed in two different programs that we call GTO. So there was some time allocated also specifically for this system because, again, it's so interesting. And I think it's going to be observed with three different instruments. One is called NIRCam, which is going to take an image probably around the 5 micron range, so in the infrared. And again, what's new about JWST compared to other instruments we're using is that it's going a little bit to longer wavelengths, where the emission from the planet will peak. So this will boost significantly our ability to see and characterize planets in general. So they will use NIRCam, they will use MIRI, which is in the mid-infrared, and I think they will also look at it with NIRSPEC, which is a spectrometer in the near-infrared, to look for emission lines, for example, coming from the two planets to try to understand maybe in the far future, the composition of their atmospheres.
Good. And Myriam, you mentioned the 40-meter telescope and adaptive optics. So you are looking forward to use one of these extreme AO, I'm assuming?
Yes, I think PDS-70 will be observed by every instrument from now on, basically. So with the extremely large telescope, we will observe it with the Maori Mikado. We will also observe it with the METIS instrument. And it's a longer time with the what we call the PCS instrument, which will be really dedicated to look at terrestrial mass planets with extreme adaptive optics. But before that, we will still use ALMA to characterize the system, because now that we have found the circumplanetary disk, we still have to characterize it and understand the physical and chemical conditions around it and in the circumplanetary disk.
So that's mean you're gonna try. That's mean you're gonna try to observe a different wavelength, for instance, to get some kind of temperature.
Exactly. So yeah, so we are going to look at different wavelengths to characterize, for example, the properties of the dust grains that we have seen there. Try to measure their sizes. Try to measure their ability to grow to small satellites. And we will also look at the gas, because so far we have this observation in the dust. But we want to understand the 3D motion of the gas around the planet and also the chemical content of this gas. And maybe Stefano can say a word about this.
Yeah.
Yes, so indeed we have available data. I mean, some of them I got literally 12 hours ago on my laptop, so I'm gonna check them very soon. So the two channels and ways we're moving forward to is, the first one is, again, the kinematics. So I'm really understanding how the planets interact with their circumstellar and disk, and possibly even trying to detect the kinematics or signature of rotation around the two planets of gas. And this will be super important, because it will be like a benchmark to understand how the dynamics of the planet disk interaction, because then we can learn how this works and then use it to interpret other systems where we don't see the planets, but we see the kinematical signature of planets. And the second thing is, again, characterizing the chemistry, as Myriam was mentioning. We have a program, so we had the paper published already, but at low angular resolution. Now we just got some high angular resolution data, a little bit lower than the image we show here, because gas is difficult to image. But we are tracing a large variety of mostly organic molecules, fairly small, but we already have signatures that the material that is likely being accreting by the two planets and thus forming their atmosphere is actually chemically evolved. For example, the carbon to oxygen ratio is particularly high, and this has a lot of consequences of the kind of atmosphere these planets are going to have. And we will be able to do these again thanks to ALMA, thanks to the incredible sensitivity of ALMA to rotational emission lines of different molecules.
Excellent. Wow, the future is bright for this system. I'm expecting maybe a special issue one day on this circumplanetary system, and probably a book will come, right? So we're gonna hand it here, but I have one more question for you, for the three of you. I would like you to answer to this question as briefly, but it's not only about science. I want to know a bit about how did you feel when you got this discovery? Maybe the one who saw the image first, for instance. Maybe you can tell us the story. And what's the next step in your career? You want to start, Myriam? It's your my top left here.
Yes. So we had observed this system since we discovered the planet. So this was already, in general, very exciting. We knew we were going to find something exciting. And then a year ago, we had evidence for the presence of dust around this planet. And this observation that we obtained were really the booming confirmation of its presence. So when we found it, of course, we were really excited. But what has been really nice, I think, in this project is that we have been working closely in a really very nice and friendly team. And that has, like the beautiful aspect of this project in general is that we have been learning a lot and collaborating through this, international collaboration, and also through the work of a PhD student. So in general, the human history around this project has been really pleasant and beautiful. And the next step is for me to go back to Europe. So I've been on a sabbatical for 4.5 years in Chile. And right now I'm looking forward to move back to Europe.
So you're going back to Grenoble, or?
Yes.
Yes, okay. Very good. What about you, Richard?
So I think when I first saw the image, it was just absolutely amazing to see that we could really detect what we're hoping to see. I mean, we've had sort of a decade of predictions of people saying this is what circumplanetary disks should look like. So to see that firsthand, that the data is showing exactly what people had predicted, that was really exciting. And I think I really want to echo Myriam's comments that this was a really excellent collaboration. Everyone was very friendly, and we spent so long trying to verify the results to make sure that what we're seeing was real. It was really amazing to have so many different experts all bringing their own expertise in to really test all the different assumptions that we're making, so we could really be as certain as we could that we were seeing what we were hoping we were seeing.
Hey, and what's the next step for you?
So I'm going to be staying around the US for a little bit. So I'll be moving to MIT actually next year. And so I'm going to continue looking at how we can use ALMA to sort of understand the initial stages of planet formation, to really understand what the building blocks are of these planets, whether we can start to do this in different systems, and to understand how we can connect that to what we see in our own solar system.
Good. And same question for you, Stefano.
Yeah, so it's difficult to answer after the two answered by Myriam and Rich, of course, but I mean, I agree with them. Sometimes in our job, I think we tend to like get used to these beautiful, outstanding images, but sometimes it's so beautiful to take a step back and realize how just beautiful and outstanding it is that we're observing dust that is likely to form moons around an exoplanet that is 400 light years away, and we're able to directly see it. And we are the first human beings in history that are doing this, and this is just mind-blowing, literally. And so to take this step back, I think has been I've been really happy and proud to do that. And let me also say that to see how people and also non-astronomers reacted to the press release we had, and see how awed and moved they were out of the beauty of this image, really struck me, and really gave me a boost in realizing how beautiful the job I do is, and also that we're able to offer this kind of image to everyone, and so that everyone can really enjoy the beauty of the sky. And And again, I also echo both Myriam and Richard in saying how beautiful it has been to work together on this particular project. Now you see the beautiful image, but I think it also had its challenging times because it did require a lot of technical work, and it's not always super fun. But still, we persevered, and at the end, we're very happy how we helped each other in the process. So I'm really happy I was part of the team.
Good. So you are going to stay at ESO for a while?
No, now I'll be moving in from the beginning of September. I'll actually go back to where I studied. So I'm moving back to Milan to start a new position here.
Wow, everybody is moving. The world of science, right? Yeah, I do remember this time. Okay, guys. Well, thank you very much. Thank you, Myriam. Thank you, Stefano. Thank you, Richard.
Thank you very much.
Thank you to all our viewers. I'm very happy we have put this SETI Live together. Frankly, that was something I really wanted to do this week before leaving Europe. So I'm glad we had the opportunity to talk about, I think, one of the best discovery of the year, but the year is not over yet. So maybe something else will come. But I'm, of course, very biased because, you know, I study exoplanets and I like imaging. And I live in Chile and I work at European Southern Observatory. So, of course, I'm biased. But yeah, it's an amazing discovery and a great, I think it's a great step in the study of exoplanets and understanding how we can form planets and moons around us. So thank you to all our viewers for watching us. This was the SETI Live. And as you know, the SETI Live is led by the SETI Institute, a nonprofit organization located in Mountain View, California. But we are everywhere in the world, as you can see. We are going to have a SETI talk in August to talk about the definition of life. So if you want to hear about what is life, understand what is life, follow our website. We're going to make an announcement pretty soon. If you are inclined, you can follow us, of course, on Twitter, YouTube, Facebook, Periscope. No, it doesn't exist anymore. Twitch, anywhere. We are everywhere. We have a website, www.seti.org. And you can get our newsletter, know about what's going on in the search for life, in the study of the universe, of course. And if you're inclined, click here and make a small donation, even 5 cents. It will help us. It will help us to travel back to California, in my case, and to all these researchers to do this amazing research here at the SETI Institute and elsewhere in the world. So thank you very much. Have a good day, evening, afternoon, wherever you are on this planet. And see you next week, maybe. Bye-bye.